Hello, everybody. And now it's section 4.2, and we're going to start off with a concept called concavity. That has nothing to do with how much you brush your teeth. It has to do with, I think I'm hilarious. Nobody else does, but I think I'm hilarious. Anyway, so if you notice it, we have a curve. Here we have a curve, and there we have a curve. So if you notice, like the cave, so to speak, is up, is facing on the top. And here the cave, if you will, is below. That's the best way I could say it. Concavity. So we use the expression. So we say. So there's an expression we use: concave up and concave down. Since the cave part is facing the top, then we say this is concave up. And for this guy over here, B, the cave part is facing down, so we call it concave down. Now, alternatively, one could say that if the tangents are on the bottom, then the cave is on the top. So the concavity is like the opposite of what the tangents are. Notice that we have a curve where it's where the tangents are on top. Here, the tangents will be on top of the curve, which means that the cave is down below it. Anyway, this is concave up, and that's concave down. That's just the way it is. So so the question is, well, let's look at some more. Let's analyze this a little bit. Notice that here, if I would draw a tangent at this point down here, the tangent would be kind of flat. Here, the tangent is getting steeper and steeper and steeper. And as I go further up this curve, the tangents keep on getting steeper and steeper. Whereas here, it's just the opposite. Here, this tangent is like straight up. And now that's, let's say, a 45-degree angle, and that's going to be a more shallow angle. So notice that when it's concave up, the tangents, the slope of the tangents is increasing. And besides the fact that the curve is increasing, but the slope of the tangents is increasing. That's really what I'm talking about right now. By the way, concave up doesn't necessarily mean that the graph will be increasing, because if I have like a parabola, so it's still concave up even on this side when the slopes are negative. But the point is that the slopes are always increasing. And here the slopes are decreasing. Now, if the slopes are increasing, that means the slopes are increasing. Well, the slope is the first derivative. Well, if it's increasing, we know if a function is increasing, that means the derivative of that function has to be positive at that, in the interval where it's increasing. Well, that means that the derivative of the first derivative must be positive. So when a curve is concave up, the derivative of the derivative has to be positive. And when a curve is concave down, the derivative of the derivative has to be negative. Now, derivative of a derivative, we just call that a second derivative. So a second derivative is not different. A second derivative is the same thing as the first derivative. The only difference is it's just a derivative of the derivative, but it's not a whole different, it's not a different process. The way you find a second derivative is the same method of how you find the first derivative. So we just call them first derivative, second derivative, because we want to really, for the purpose that we're going to learn in this chapter. Anyway, moving on. All right, so again, notice that the tangents are beneath the curve. Here, the tangents are above the curve, and you see how the tangents are growing. That has the slope of the tangents. That has a slope of 0.5, a slope of 1, a slope of 1.5, a slope of 2, and here is a slope of 0.25, 0.5, 0.75, 1. So you see that well, I'm sorry, I'm in the wrong place. 1, 0.7, 0.6, 0.5. So notice that these numbers here are decreasing, and over here, the numbers are increasing, 0.51, 1.52, and here it's 1, 0.7, 0.6, 0.5, and so on and so forth. And now we have a definition down here in the bottom. The graph of a function is concave upward on the interval of AB if f prime of x is increasing on AB. That's actually a definition we're giving for concavity, and is concave downward on the interval if f prime is decreasing. Well, this is going to lead right into what I was just saying before about second derivatives, because because the second derivative, if y equals f of x, the second derivative of f, of course, provided it exists, has to exist. By definition, that's just that's a notation. We call it f double prime. We just write f prime prime. Or if you're using this notation, we say d squared y dx squared. I'm not actually squaring anything, but it's just a second derivative. And so it's just so f prime prime is just the derivative of the derivative. And as we're going to see, there's a well, we'll see all that. Okay, so let's just summarize here. For the interval AB, if f double prime is greater than 0, then f is concave upward, which is what I was saying, because we were explaining that, because if f double prime is positive, that means that the first derivative is increasing, and the derivative of that derivative is positive. And when that happens, f is the function, the original function f is concave upward. And if f double prime is less than 0, then f is concave downward. Now I want to take a moment now to say, I said this in the last section, I'm going to say it now. One of the reasons, in my experience, that students have difficulty with this is because they start getting, we're talking about the function f, and then we'll talk about the derivative f prime, then we'll talk about the second derivative f double prime. And we have, and all of these are individual functions. F is a function, f prime is a function, f double prime is a different function. So we have all these different functions showing us all these different things. And sometimes students kind of get lost in the sauce. And we're talking about because we're using the second derivative to tell us about the first derivative, which tells us about the function itself, and the function tells us about the derivative. There's just so much going on that sometimes students get lost because they don't know, or they lose track of what's referring to what. And I'm only telling you to be aware of that. If you're aware of it, you could just, make sure you always know what's, if you're aware of it, it'll help you. I can't explain it, but if you're aware that this is something where people get lost and confused, you'll like Hansel and Gretel left breadcrumbs, you'll figure out what to do. But you ever hear of Hansel and Gretel's story? Anyway, so if f double prime is positive, that means f single prime is increasing, which means the f itself is concave up. And if f double prime is negative, that means f single prime is decreasing, which means f itself is concave up. F of x itself is concave downwards. And that is the story. And I'm sticking to it. So here we have some examples. We have some examples of functions. And let's just see, for example, right. Now, notice over here, on this guy here, it looks kind of like a parabola. I don't know if it is a parabola, it looks kind of parabola-ish. So if I would draw a tangent over here, the tangent would be negative. I never said a tangent can't be negative. The tangents just have to be increasing. So this could be like -5, then it's -4, then it's -1, then it becomes 0, then it becomes 1, then 2, then 3, so on and so forth. And that's important. If f double prime is positive, it doesn't mean that f single prime is positive. You see what I'm saying? It just means that f single prime is increasing. But it could be negative. It's just becoming a smaller negative as we go from left to right. And here too, f double prime is negative down here, even though the derivatives here, at least on the left side here, are positive. But they're becoming smaller positive numbers till they finally hit 0. Then they become negative. Then they start becoming bigger negative numbers, and that's because it becomes steeper. So that's really what's happening here. How do I know it's becoming steeper? Because that's what a curve is. The curve moves, and that's important to realize. Alrighty, let's do an example. So we want to find the intervals on which notice I said which, not which the graph of each function is concave upward, and the intervals on which it is, and we want to find where it's concave downward. So we want to find both those things based on some calculus. So what we're going to do, we have a is e to the x, b is ln x, and c is x to the third power. So we're going to do some math here. Actually, we're going to do some calculus crunching. So the derivative of e to the x is e to the x, and the derivative of e to the x is also e to the x. Now, e to the x is always positive. Whenever you have an exponential function, it's always positive. E to a power is always going to, no matter what the power is, because if x is negative, I don't get a negative answer. I just get a reciprocal answer. I just get a very small positive number. Now, for ln x, the derivative of ln x is 1 over x, and the derivative of 1 over x is negative 1 over x squared. And I just want to go through all these and we'll analyze them all. The derivative of x to the third is 3x squared. The derivative of 3x squared is 6x. Now, let's look at this. E to the x, as I said, is always positive, which means the function, the graph, is going to be always concave up for the entire graph. And that you see, let me see if I can just get this. Okay. So e to the x, I'm looking down here at f double prime. E to the x is always positive, which means the graph is always, and that's true if you look at the graph, it's always concave up the entire thing. Now, x squared is always positive. When you square something, it's always positive. And this can never be 0, because I can't have 1 over x squared, even if x is, well, if x is 0, then it'll be undefined. There's no value that actually makes it 0. So this is always, so x squared is always going to be positive, or 1 over x squared is always going to be positive, but it's negative 1 over x squared, so it's going to be always negative, which means the ln graph will be concave down for its entirety, which, as you see, that's the case. This is always concave down. Although notice that when x gets very big, the ln graph kind of plateaus. It's always rising, but it rises in a more shallow way, which means as x gets very big, the second derivative gets closer to 0. It never hits 0, but it gets closer and closer to 0, which means this kind of shallows out. It does rise forever. It does keep on rising forever, but it shallows out. It just rises less steeply. I don't know, say, what's the word for less steep? Shallow? I don't know. Anyway, now for this guy, the second derivative is 6x. Well, 6x is always negative if x is negative, and 6x is positive if x is positive. Now notice that the first derivative, 3x squared, that's always positive. So this always has tangents. This curve will always have tangents with slopes pointing up, but they're going to point up less when x is negative and then start pointing up more when x is positive. And they're going to be concave down when x is negative, concave up when x is positive. Look what we have right here is the graph. So this is concave down at this point, and the slopes are decreasing, because here the slopes are very steep, and then become a little more horizontal. Here the slopes actually horizontal, and then it starts picking up and going up. So the slopes are decreasing for the negative values of x, which is why it's concave down, and then the slopes start to increase for the positive values of x. Now the tangents happen to always be positive, except at 0, then it's 0. But the tangents are never negative. They're always, because 3x squared is never negative. 3x squared can be 0, but it can never be negative. And that's so a picture's worth 1,000 words. Okay. Now there's something called an inflection point. Okay. So if you notice, here is concave down. Let's look at this third example. Here's concave down, and then it switches to become concave up. When a graph when a graph is concave down, and then it switches to be concave up, or vice versa, if it switches from up to down, or that point where it switches, we call that a point of inflection. So it's concave down, and then at 0, it switches to concave up. So x equals 0 is the point of inflection for this graph. And like I say, we could have a graph that goes from concave up, concave down. Let's do a quick graph on I'll just give an example here. Let's just do a quick graph on decimals. Let's see, y equals, I don't know, I'm gonna do it this way. This is gonna be what I want. X minus 1 times x plus 1, x plus 1, and x minus 2. Okay, so right around here, right around that point right there, notice on this side it's concave down, and then on this side is cut. And that point is, I'm going to say x equals 1. I don't know if x equals 1. I don't know if it's exactly x equals 1, but it's somewhere around x equals 1. Everything on this side is concave up. Everything on that side, that's a point of inflection where it's going from concave down to concave up. Now, of course, if I would just make this whole thing, let's multiply by x. Now here, we're again roughly around here. I can't, it's a little hard to tell. Here it's concave up, and now around here it becomes concave down, and here it becomes concave up again. So this point where it switches from up to down, that's a point of inflection, and this point over here where it switches from down to up is a point of inflection. Now, what's the exact point? We're going to use calculus to figure that out. Here I'm just kind of eyeballing it. But with calculus, we can get a precise fix on where that point is. So that's the evil plan of today. Alrighty. So let's point inflection. So C comma f of C, that's the point. So I was talking about the x value, but f of C is the y value. Is if C is an inflection point, then C is a partition number for f double prime. C is an inflection. So let's look over here. An inflection point is a point on a graph of a function where the function is continuous and the concavity changes either from upward to downward or from downward to upward. And for the concavity to change at a point, f double prime has to change sign. So f double prime, right? Because when it's upward, it's positive, and when it's downward, it's negative. So f double prime obviously changes at that point. So these are the things we see. And of course, partition numbers help us. They identify where points in a function can change sign. So if CFC is an inflection point, that means C is a partition number of f double prime. Again, these are just I'm just throwing more words at you with the partitions and flex, but that's the point. Where concavity is. Let's look at an example. I'm getting flustered. That's what happens. What can I say when you're in love? I love math, so I talk fast. I get very excited. I get flustered. So let's just, I gotta do some yoga. Namaste, much better. So to test for inflection points, you want to find all the partition numbers of f double prime, and f has to be continuous at C, which means f has to be obviously defined at C. For each of these partition numbers, you want to make a sign chart of f double prime near x equals C. And notice that here I have f double prime, here I have f itself. So that's again, we're switching back and forth from the function to the derivative to the second derivative because we're using the first and second derivatives to teach us things about the function itself. Anyway, if the sign chart of f double prime changes sign at C, then C comma f of C is an inflection point of C. If the sign chart does not change sign at C, then it's not an inflection point. Meaning that you can have a partition just because the value is 0, but just because it's 0, it doesn't mean it's gonna inflect. It may just become 0 and then go back to staying 0 at that point. It means stay back whatever it started. It started at positive, it went down to 0, then it became positive again. So it didn't change sign. So let's just look at some examples here. So here we see it's positive up to that point, then it becomes negative. This is a point of inflection. Here it's negative up to this point here, whatever that point C is. And here it's positive after that point. This is a point of inflection. Here it goes from positive, and at that point C, it switches to negative. And here, it's going from negative to positive. So it is concave down and concave up. However, it's not defined because the function is defined, but the first derivative is not defined because the tangent would be vertical. So sorry about that. So even though geometrically in a way it kind of is from a geometric point of view, it's interesting. From a geometric point of view, it kind of is a point of inflection, but it's officially not because the slope is undefined. But if I would sort of rotate this curve, now it would be and just to make the derivative not infinite, not vertical at that point, just make the tangent non-vertical, then that's the same curve, you know, or like a congruent curve that's just rotated a little bit, now be a point of inflection. I'm just saying that as a side point. Anyway, let's locate some point of inflections. And first of all, if you have a point of inflection, you shouldn't lose it. So you shouldn't have to rotate it, locate it. But now I have a thing on my phone, Google Location, where I can locate things. But we're going to do this just with math. Now, we're not going to use computers. We're just going to use plain old math. So our function f of x is x cubed minus 6x squared plus 9x plus 1. And we're looking at some point. So we want to see where f double prime changes sign. Now, there's no way I can know if f double prime changes sign unless I know what f double prime is. So I'm going to have to take a derivative of this function here, and then I'm going to take the derivative of the derivative. So the first derivative, then the second derivative. Well, the derivative of x cubed is 3x squared. The derivative of minus 6x squared is negative 12x. The derivative of 9x is 9, and the derivative of 1, that's just 0, just takes a vacation. And the derivative of 3x squared is 6x, negative 12x is negative 12, and that's it, we're done. And notice we factored out the 6 here. It just makes it easier, because that makes it more clear that 2 is going to be my inflection point. X equals 2 is going to be my inflection point. So we took the function, we took the derivative. Now the derivative itself teaches us a lot of things about the function, and which right now I'm kind of conveniently ignoring. Although we are going to put all this stuff together. We're gonna look at the function, the first derivative, and the derivative, and the second derivative, and we're going to put all that information together and get a handle on what the graph of the function looks like. Which is, so we're going to be a lot of detective work, but we'll just one step at a time, one thing at a time. So my sign chart will be, it's negative, 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 until it hits x equals 2, then it becomes 0, because 2 minus 2 is 0. I'm looking right over here. And then after that point, it becomes positive. So if x is like 0, I have 0 minus 2 is negative. If x is 5, 5 minus 2 is 3, it's positive. So that's the story. So 2 is that cutoff point. And you see we tested something. We tested 3 and 1, because 1 minus 2 is negative 1, and 3 minus 2 is positive 1, and whatever that. So we see it's going to be negative here and positive there. And again, this is a way of testing stuff that you learned in algebra. Okay, moving on. So we see that 2 comma f of 2, which is 2 comma 3, is the inflection point. Now, how do you know it's where the 3 come from? Well, if you take 2 and plug it in for x and crunch it out, you wind up getting 3. So what I would like to do is go back to Desmos. I want to see if this is real. Now, what's interesting here, what's fascinating to me here, is that we finished the problem. We know the inflection point 2 comma 3. Yet we never graphed this function. I don't even know what this function looks like. So let's graph it. Let's test this out. Let's see if this stuff like actually works. Who knows? Maybe it'll actually work. So now what am I going to put into Desmos? I'm going to put in the original function. And what was that original function? X to the third. Let's see. X to the third. Let's start with that. Remember that part. X to the third minus 6x squared plus 9x plus 1. Minus 6x squared plus 9x plus 1. Okay, and I want to look at the point. Let me move my beautiful picture away. I want to look at this next point here, which is just the point 2 comma 3. 2 comma 3, and look at that. Look how beautiful that right there. So the point 2 comma 3, that's my, what happens if I kill label? Oh, okay. So the point 2 comma 3, that's my inflection point. Notice that the graph is concave down before that point, and now it becomes concave up after that point, which we saw in our chart. It went from negative to positive, and here we see it in the picture. So a picture is worth 1,000 chihuahuas. That's all I can say. Pictures. Now, did we have to do the Desmos thing? No. We actually we could have just solved this with the just the calculus that we were crunching out, just this, you know. But again, I want you to see how this stuff actually works, and when you draw it, when you actually graph it, you actually get somewhere. There's a certain, I want you to see the consistency of math. I want you to see this stuff actually works, because as I don't have to tell you all, this calculus can get very, you know, theoretical, and therefore I always want to bring it back to something that you could grasp and picture. I've found in math, again, now I'm just talking my experience again, I found that students do well in math until they get to a point where they can no longer picture what it is that they're doing. Once you lose that visual, once you lose that picture of what's going on, that's when students start dropping out. So a lot of times you see students saying, well, I was great in arithmetic, but then when I got to algebra, or I was great in geometry, but when I got to trigonometry, people say, oh, I was great in this, but then when I got to calculus, oh, I got so, because what happens is, in my experience, when you get to points of the more abstract it gets, you start to lose a picture of what's going on, the concrete picture of what's going on. You start to get more lost. Some people are the opposite. Those people are called freaks, like me. I'm that's what I am. Meaning that I actually did not do well in math, like in arithmetic. I actually did better in math when it got more abstract. It's interesting. People's brains. And that's what makes life interesting. So let's go back to the textbook and let's continue. Let's carry on. Here we go. So let's go to the next example. It's been loads of fun, and we're going to continue. Okay, let's look at another case. We want to find the inflection points of f of x, which is equal to ln of x squared minus 4x plus 5. So again, we want to find, inflection points just means where the second derivative goes from negative to positive, and that's what we're going to do here. So first we want to find the domain, because the log, as we know, or the ln, is only defined when the domain is positive. So I need to know when this inner part, x squared minus 4x plus 5, I need to know when it's positive. So I want to know when x squared minus 4x plus 5 is greater than 0, and this is equal to this. In other words, I'm rewriting the parabola in this way, and that tells me that this is true. This tells me that this parabola is going to be always positive, because x minus 2 squared is never negative. It could be 0, but it's never negative. But even if it's even if it is 0, I always have the plus 1, which makes it positive. So this inner part here is always going to be positive. If you graph it, it will be a parabola that's like up in the air, and it never touches the x-axis. And in fact, don't take my word for it. Let me show you that. I'm looking at this inner function, x squared minus 4x plus 5. Let's just graph that. Okay, so we don't need this anymore. So x squared, y equals x squared minus 4x plus 5. So it's a parabola that never touches the 0. And notice that the vertex of the parabola is 2, 1, which makes sense, because the x minus 2 tells you that x equals 2 is the low point, which you see right here, and the 1 is the 2, 1 is the vertex. That we know from algebra. Anyway, let's go back to where we just were. F prime. Okay, so f of x is this ln function. Okay, and I will graph this on Desmos, but let's just do it purely with algebra without even looking at a graph. And then later we'll look at the graph. So we know that this is going to be 2x minus 4, because that's the inner derivative, over x squared minus 4x plus 5. Okay, and here's where it starts to get really fun. Now, to take the second derivative, this is a quotient, so I need the quotient rule. So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So I have here, we have to, so the derivative of 2x minus 4 is just 2, and the derivative of x squared minus 4x plus 5 is 2x minus 4. So I got to do a whole bunch of multiplying. So I get, this becomes 2x squared minus 8x plus 10. That's why I get this over here. And now when I multiply this out, kind of FOIL it out, I get 4x squared plus 16x minus 16, because everything I get from this FOIL, I have to negativize it. And now we're combining like terms, and we have negative 2x squared plus 8x minus 6. I'm factoring out the negative 2 because I want to see what this thing looks like. And I get negative 2 times x minus 1 times x minus 3. And that tells me now the bottom is always positive. We already established that. First of all, even if x squared minus 4x plus 5 was not always positive, since I'm squaring it, it's always going to be positive. In fact, and it's never going to be 0, so it's never going to be undefined. So we're all good with that. Now what I have to look at. Now once I have this here, x minus 1, x minus 3, that tells me that my partition numbers are going to be x equals 1 and x equals 3, because those are the things that make this top guy 0. Like I said, the bottom is never 0, and in fact, it's always positive. So it's almost like a non-factor in the sense that it doesn't affect the positivity, negativity. Anyway, complete it, get a couple of, whatever you call it, test points. So since 1 and 3 are the partitions, we'll look at 0, 2, and 4. And when you get 0, 2, and 4, we plug in 0, you get negative 6 over 25, and you plug 2. Now, where am I plugging it into? I'm plugging it into f double prime. I'm not plugging it into the original function. I'm plugging it into f double prime. And when I plug in, I get a positive number, and I get 4, I get a negative number. So this is going from negative to negative, which means 0, which means x equals 1 would be a point of inflection, and x equals 3 would be a point of inflection. And they are on the, and everything here is defined. Everything is beautiful. So the sign chart has inflection points at x equals 1 and x equals 3. Since f of 1 equals ln 2 and f of 3 equals ln 2, the inflection points are 1 comma ln 2 and 3 comma ln 2. I'm going to put this all in Desmos and you'll see it. But before I do that, I wanted to make a point. Actually, you know what? Let me do that first, and I'm going to come back and make my point. Let me finish the whole problem, and then I'm going to come back and make the point I want to make. So let's look at the original thing, ln of x squared minus 4x plus 5. So let's go to Desmos. I'm just going to so y is equal to ln of this, and this is what it looks like, and we want the point 1 comma L and 2, and we want the point 3 comma Ln 2, and let's label that. And if you notice here, it's by looking at the graph, here is concave down, here it switches to concave up, and now it's back to concave down. So that's kind of cool and awesome. So again, Desmos sort of bears out what we saw in the in our theory. And now I want to make my little speech, my side point, which is something I kind of touched on, but you really see a great example of that in this problem right here. Okay, so here's what I'm trying to say. I had mentioned before that I'm not going to absolutely require you to simplify your answers. You can get a big messy out, like for example, over here, f double prime. So the second line here, this you can't have because I have derivatives. You have to get rid of all the derivatives. But once you get to this line right over here, where my cursor is, really you could leave it like that, and it's technically the correct answer. Or you could have just done this step and left it that way, or you could have just done that and left it that way. You didn't, or you could go all the way to the end, but you don't really have to go all the way to the end, to get credit for solving it. However, here's my big, well, not how, I shouldn't say however. The thing is like this. In this, sometimes, such as this example right here, if I would have left it like this, then it would not be evident what the partition numbers are. You see what I'm saying? So even though I'm not I'm doing air quotes now, I'm not requiring you to simplify your answers. If you don't simplify it sometimes, you're not going to get to what you want, because I can't look at this and see what the partition numbers are. I can't look at any of these. It's really not till I get down to the bottom. It's not really till I get down to the bottom one that I could see right away x equals 1 and x equals 3. Those are my partition numbers. So I need that. Simplification for my answer. Plus, there might be times, you never know, where you're asked, let's say you're asked to find a third derivative. Well, if I have a third derivative, you definitely want to simplify my answer as much as possible to make the third derivative. Because if I have if I leave it like this, and now I want to take a third derivative, which means take a derivative of this guy, it's going to be a big unwieldy mess. So sometimes you want to simplify it and make it more compact, either because it's going to show you critical information, or because you want it more compact. So then if you go take another derivative, it'll be more, work better for you. So yes, technically, I'm not going to require you to simplify things, but there will be times when it is very much in your best interest to simplify, so that so you can get whatever it is that you're trying to accomplish. And that's all I'm going to say at this. That's all I'm going to say on that. Now we're just going to move on. Before we go on to the next example, I want to make an important point, and you really see it down here in this conceptual insight, that the partition numbers are only candidates for inflection points, meaning that if the second derivative equals 0, that just means that that point could be an inflection point. It doesn't mean that it always is. And a couple of good examples here is if f of x equals x to the fourth, then f double prime is 12x squared, which is always equals 0 and x equals 0. And if g of x equals 1 over x, then g double prime is going to be 2 over x to the third. So in each case, x equals 0 is our partition number. However, it is not a point of inflection. See over here, I see 12x squared is always, well, this is x to the fourth, but the second derivative of 12x squared is always positive, so it's concave up here, concave up there. So even though the derivative is 0, the slope of the tangent is 0, but nonetheless it's not an inflection point. And here for 1 over x, this is the graph of 1 over x. So yeah, it's concave down. So it's going from concave up and staying concave up. Here it's going from concave down to concave up, but the graph is discontinuous at x equals 0. It's not defined at x equals 0. So just because you get one of these, so when the second derivative equals, the point is that it's not always you can't just go, okay, I'm going to take derivatives. You have to check it out. You have to check it out. That's what I'm trying to say, in a little common sense. Okay, so let's just look over here. In other words, even though g is going from concave down to concave up, it's not an inflection point because g of 0 is not defined. This is what we're saying over here. Okay, let's look at the next example. Here we go. Here we have a graph. And you can see how it's concave down here, concave up there. But let's just look at this. Let's use the graph of f and include a sketch of a. Oh, sorry. This figure here is not f. This figure here is the derivative of a function f. And we want to use the graph to figure out stuff about f itself. And we want to sketch a possible graph of f. In other words, this here is not f, but it's the derivative of f. But we can learn things because, like here, for example, when the derivative is above the x-axis, it's positive, so the function is increasing. Here, the function is decreasing. Even, because everywhere here the function is decreasing. The derivative is increasing, so so that means the second derivative is positive. So we're going to learn a whole bunch of things. We're going to look at everything here and put it all together and get some possible sketch of what the graph of f looks like. That's what we want to do right now. So notice that from this part right here, from negative infinity up to x equals -2, so the derivative is negative, but it's also increasing, which means that because it's negative, that means the function is decreasing, and it's also going to be concave upward. Because of it, not because of the negative part, but because of the increasing part. And the negative part means it's decreasing, that the original function is decreasing, and the increasing part means that the original function is concave up. Now, the derivative is increasing, and now at this point it starts decreasing. So that means it's going from concave up to concave down. Not that this graph that we're looking at is going from concave up to concave down, but the original graph has to be concave up to concave down, because if f is increasing, if f prime is increasing, then f double prime is positive, and when f prime is decreasing, f double prime is negative. So so therefore it's going from concave up to concave down. See how much fun this is? When x is when x is -2, I'm going to have the function has a local max, which means the derivative has a local max, which means that the x equals -2 must be an inflection point, because if the derivative has a local max, that means the second derivative is going from positive to negative, it's changing sign. Between -2 and 0, the function is negative and decreasing. The derivative, I should say, is negative and decreasing, which means the original function has to be negative, because has to be decreasing. I'm sorry, because of the negative slope, and it's concave down because a decreasing first derivative means a negative second derivative is concave down. X equals 0 is a local minimum for the same reason that -2 is a local max, because it's changing direction. It's going from negative to positive, and so it's going from concave. It's going from it's going from downward to upward, and it's an inflection point. And now it's from here in this little stretch from 0 to 1, the derivative is still negative, but it's increasing. So the function itself is decreasing, but it is concave up. And when x equals 1, that's the X-intercept, which means that's a local minimum. And why is that? Because if the first derivative is equal to 0, then the function itself has a local minimum. And also the derivative itself is changing signs. That's the first derivative test. And finally, between 1 and infinity, when x is between 1 and infinity, the f prime is positive and it's increasing. So because it's positive, that means the original function is increasing. Because it's increasing, that means the original function is concave up. And here we have on the side a possible graph which satisfies all of these conditions. And notice that over here, the derivative is negative, yet here the function is way up here, a high positive. Because it's not because the negative derivative doesn't mean the function is negative. It just means the function is decreasing. And you got to realize that. So it's a lot. So this is this is how it all works, and it's all beautiful. Okay, let's look at another problem now. So now we're going to get to something called curve sketching, meaning that we're going to look at the information that we can get from a first derivative and a second derivative and all this kind of cool stuff that we've been doing, and use all that to figure out what the graph of a function looks like. Now, you're used to just saying, hey, I'm just going to take the function and plug it into Desmos, everything's cool, I don't have to, but, you know, well, first of all, computers and calculators, a lot of times they just do it they just plot, you know, computers. One of my best and most favorite math professors told me that a computer is just a very fast idiot, meaning that the computer doesn't really analyze and know what it's doing. It just, if you give it a function, it'll just start, since it's so fast, it'll just plot like zillions of points. And you see this like nice smooth curve on the Desmos or on your graphing calculator or whatever it is that you're using. And, but we're going to use some old-fashioned cleverness and creativity. And this is something that was done for, you know, it's, I guess now, you know, when I was in school, this was cutting edge, you know. Now it's like old school, because the idea of actually using your brains instead of just using a calculator. Oops, I just made a little dig there. So, but seriously, you need to, you know, you need to understand the math behind what's going on. If you don't understand what's behind it, then what do you have? The more you understand, let's put it this way, the more you understand, the easier the math is going to be, and the less it's going to feel mathy, if that makes any sense. Alrighty. So, oh, by the way, I just was taught a acronym of what math stands for. So hold on one second. Let me just pull it up here. I'm gonna type it here in our little thing. Where is it? So here's our Google Doc here. So here's math. I was just taught this. M-A-T-H. Okay. And let's make this nice and let's make this nice and big here. It's very important. As you can see, we always do very important work here. So now you know what math stands for. So this acronym tells you what math stands for. Now you know, mental abuse to humans. Alrighty. So let's go back to where we were here. So, oops, let's go back to right here. Okay. So this is the procedure that we're going to use for strategy, the strategy for graphing. So we're going to find, so when you have a function f of x, so the first thing we do is we look at the domain, want to find the domain, the intercepts, the x-intercepts, the y-intercepts. You want to find all this stuff. In other words, basically, you want to do all the stuff that you could do without calculus. All the stuff that you could do just using algebra, you want to do that first and get as much information as you can about this graph. Then you want to look at the first derivatives. You want to find the partition numbers, the critical numbers. You want to make a sign chart. You want to see where it's increasing, where it's decreasing, where the maximums, minimums, all that kind of stuff are. Then you want to look at the second derivative, find the partition numbers for the second derivative, again, make a sign chart, and you want to see when is the graph, by looking at positive, negative, you want to see when is it concave up, when is it concave down. You want to see where are there points of inflection. And that's when the concavity changes from up to down or down to up. And then finally, you put all this information together and we sketch the graph. And we're going to find the intercepts and the maximums and the minimums and the inflection points and all that kind of cool stuff that we've been doing. We're going to concavity, all that kind of stuff. All that stuff we're going to do with the graph. So basically, we're going to look at so first we look at the original function and just do everything we can with algebra and graphing and all the things that we learned back in algebra and graphing. Then we're going to look at the first derivative and everything that teaches us, and the second derivative and everything that teaches us, or informs us, I should say. And then finally, we're going to put all that together and sketch the graph. That's curve sketching. This, I have to say, I will say, this is always my favorite topic in calculus, is curve sketching, because it's like you're literally being a detective, and you're using the detective powers to put together all this information and make a beautiful picture out of it. All right, so we want to look at x to the fourth minus 2x to the third. X to the fourth minus 2x to the third. We want to use our powers to graph that. So this is interesting because to find the x-intercept, I set the function equal to 0, which means x to the fourth minus 2x cubed equals 0. And then I factor out x cubed times x minus 2 equals 0, which means I get x equals 0 is one time, is going to be one x-intercept, and x equals 2 is going to be a different x-intercept. Now, to find the function for y-intercept, I just plug 0 into the function and see what I get. Well, if I plug 0 here, I get 0 minus 0, so I get 0. Well, so that means if x is 0, y is 0, which means 0, 0 is a y-intercept, but really 0, 0 is an x-intercept also. So even though I have 1, 2, 3 answers, it's really just 2 answers, because the first x-intercept is also the y-intercept. So this is 0, 0, and this guy over here is 2, 0. How do we know it's 2, 0? That's what an x-intercept is when y equals 0. So that's so we know that there are 2 intercepts. It goes to the origin and it goes to 2, 0. Those are the only intercepts. And now that's algebra. Now we're gonna go to step 2, which is calculus. Okay, let's go to step 2, which is a little calculus. Now we're gonna look at the first derivative. Well, the first derivative, if I differentiate my original function, I get 4x to the third minus 6x squared, and I can factor out a 4x to 4x squared, and I get x minus 3/2. Now the reason I want to factor this stuff out is because this way I could easily see when this guy equals 0. Well, the partition numbers are going to be x equals 0 and x equals 3/2, 3/2. The critical numbers So that's the partition numbers for f prime, which is and that's the critical numbers for 0 and for f itself. And by the way, if you don't like the fact that here we call them partition numbers, there we call them critical numbers, I got to be honest with you, it bugs me also. What do you need 5,000 names for the same idea? As long as you understand the concept, don't worry about the names. All right, or don't get hung up in the names, I should say. So let's look at the sign chart now for f prime. So if I do some test numbers, so -1 is less than 0, 1 is between 0 and 3/2, and 2 is bigger than 3/2. So I have negative, negative, positive is what I get here, negative, negative, positive. So it's decreasing, decreasing, and now increasing, which means that f of x is decreasing from negative infinity all the way to 3/2, and now it starts increasing at 3/2 all the way to infinity, which means there's a local min at 3/2. And the value of the y value at that min, f of 3/2, is negative 27/16. So notice that 0, even though the derivative equals 0 when x equals 1, that's not going to be a min or a max because the first derivative does not change signs. Step 3. Now we're going to look at what we can learn from the second derivative. Oh, look at that, they graph it for us. I don't think it does us. So f double prime, if I take the derivative of the derivative, I get 12x squared minus 12x, which factors to 12x times x minus 1. So I get 0 and I get 1, positive 1 as partition numbers. So here's my sign chart for, and again, I'm going to take -1, 1/2, and 2 to be my test numbers. And I have positive, negative, positive. So the graph is going from concave up to concave down, back to concave up. So 1 and 3 are partition numbers. I'm sorry, points of inflection. Points of inflection, that's what I meant to say. And now putting all this together, this is what I get. It's concave up. It switches concavity at x equals 0. That we said that was a point of inflection. It's concave down. Now here it switches to concave up. So x equals positive 1 is another point of inflection. Notice that at x equals 0, it comes here, the tangent kind of flattens out, but instead of going back up to make this a min, it totters for a split second and then starts going down. So I never actually have that's why I never actually had a min or a max over here. Whereas here, it went down and it came back up. So that's why I had a min, and of course it's all concave up over here. So this is all you could draw this by hand without a graphing calculator or anything, just with the calculus. So we can identify exactly what the points of inflection are. Because in fact, the truth is, if I would just show you the picture, it's hard to see exactly where the point of inflection. You can see roughly where it is, but with calculus, you can actually find exactly precisely where the point of inflection is. So that is a very good thing. That's quite amazing. Okay, everybody, this is okay, here's another cool and awesome example. F of x is equal to 3 times x to the 5/3 power minus 20x. So first step, again, we just start with good old-fashioned algebra, graphing. What do you call it? What do you call it? Not algebra. Analytical geometry, they call it. Graphing. Graphing. If you think about it, graphing is like a marriage between algebra and geometry. I mean, we're taking algebra equations and we're representing them as geometric figures, or we're looking at geometric figures and finding the algebra equations that describe them, whichever way you want to say it. But it's kind of a marriage between algebra and geometry. Anyway, so let's just use whatever algebra we can. So first we want to look at f of x is this guy right here. So what I want to do is I want to find the x-intercept. So I take this function and set it equal to 0. Well, when I set it equal to 0 to find the intercepts, I factor out 3x because I want to have just a plain lead with just a plain x. When I factor out 3x, the x to the 5/3 becomes x to the 2/3, and the 20x becomes 20 divided by 3. Right, when I pull the 3x out. If I would distribute this 3x, I would get back to what I originally started with. Now this here, x to the 2/3, that's really a perfect, that's really a square because it's x to the 3rd squared. So this is kind of like the difference of two squares, even though 20/3 is not a perfect square, but we're going to use square root-y stuff. So this factors now into 3x times x to the 1/3 minus square root of 20/3 times x to the 1/3 plus rad 20/3. And we're setting that equal to 0. The x-intercepts are x equals 0, x equals 20/3 cubed, because if x cubed equals rad 20/3, that means x equals rad 20/3 to the 3rd power. And that's approximately, if you crunch this with the calculator, that's approximately 17.21. And or x could be negative that, which is negative 17.21. And the y-intercept is just 0. So which of course is one of the x-intercepts. So really there are three x-intercepts. One of those x-intercepts is also the y-intercept. So we just have 3 different intercepts here, not 4. Because the y-intercept and one of the x-intercepts is the same thing, same point, 0, 0. And now let's do some calculus. That was all, so step 1 was all algebra. Now we're going to finally use some calculus. We're going to look at the first derivative. So when we take the derivative of the original function, we get 5x to the 2/3 power minus 20. And I'm pulling out a 5. And I'm going to factor this the way I factored the other guy. So it's x to the 3rd minus 2 times x to the 3rd plus 2. And again, if I would multiply these foils together, I would get this guy right up here. So the partition numbers for f prime is the 2 to the 3rd power, which is 8, or negative 2 to the 3rd power, which is negative 8. Those are my partition numbers. And the critical numbers of the function are negative 8, 8. All right, that is a good thing to know. And we're going to make a sign chart to see if these are indeed, maxes and mins and all that kind of cool stuff. Let's go on to the next part. So here's our sign chart. So here from 0 to negative 8, and again, we take these test points, negative 12, 0, and positive 12. And it's positive. Is this a typo? Yeah, this is a typo because it's going from positive to negative to positive, which means that should really be positive and increasing. That should be negative and that should be positive. And it even says local minimum. The reason it says local minimum is because that's what it's supposed to say. So this part here, where it says decreasing, they have all those negatives, that's a typo. That really should be positives. In fact, it even says f is increasing on negative infinity, negative 8. So this is just a typo. Please beware, typo. I don't know how to say it any better than that, but this is a little typo. And so we have a min at negative 8, and we have well, that shouldn't be a min. That should be, if it's going from positive to negative, that's a max. We have a max at negative 8 and a min at positive 8. I'd love to see the graph of this, which we will soon. So, and even down here, it even says that it's a max. So we just got a bunch of typos here. Sorry about that, a bunch of typos. But the words here are correct. Now we go to the second derivative. So if f prime is this, f double prime is going to be 10/3 x to the negative 3rd period, which is 10 over x to the negative 1/3. And this never equals 0, but it is undefined when x equals 0. So x equals 0 is a partition number, and we see that the curve goes from concave down to concave up. I can't really call it I mean that's a matter of semantics, whether you call this a point of inflection or not, but it's not defined at that point, so I don't know why you call it a point of inflection, unless that's another typo, I don't know. Anyway, so it's concave down, and then it switches to concave up, and well, even though on the other hand, even though the derivative is undefined at x equals 0, but the function itself is defined at x equals 0. So that's why it's a good point of inflection. It's not a typo. It should be. That is the way it should be. And finally, the sketch of the graph, that's negative 8, and that's positive 8, That's 0. That's a point of inflection, and it's increasing, decreasing, increasing again. And this is like a kind of like, it looks kind of like a basic third degree. It looks a lot like just a regular third degree equation, and that, my friend, is the story. But again, I just want to say that the graph is correct. Step 3 is correct. Just step 2 has a typo in the picture, not in the words, but in the picture is a little messed up. Okay. So now we're going to go to. Let's just look down at the bottom here where it says point of diminishing returns. You've probably all heard that expression, point of diminishing returns. So let's read this here. If a company decides to increase spending on advertising, it would expect sales to increase, right? You advertise more, sales increase. That's the whole point of it. At first, sales are going to increase at an increasing rate, but then it's going to increase at a decrease. I mean, if you keep on advertising, it gets to a point where you're just spending so much money advertising, and it will give you more business, but not that much more. You know, it's a point where it becomes like a waste. Well, they call it diminishing returns. In other words, yeah, if I advertise more, I've saturated the advertising market so much that, yeah, I can still get more sales, but it's not as dramatic an effect as so those first advertising dollars produce a very dramatic effect. I got what they call a big bang for my buck, but the next advertising dollars are diminishing. Well, that means that the rate of change of sales goes from increasing to decrease. Not that sales goes from increasing to decreasing, but the rate of change, meaning that it was changing fast, and now it's changing. It's slowing down. So if the rate is decreasing, that doesn't mean that the sales is decreasing. It just means the sales is still increasing, but it's not increasing as fast. And that's called the point of diminishing returns, not the point of no return, not the point of reverse, but just point of diminishing returns. I'm just not getting the same bang for my buck. Well, this sounds very second derivative-ish to me, and point of inflection-ish for me. And guess what? That's exactly what it's going to be. So let's look at an example. And like I say, money spent beyond this point of diminishing returns may increase sales. It can still increase sales, but at a lower rate. It won't be as dramatic. The effect won't be as dramatic. And it could even get to a point where the increase in sales is not worth the cost of the advertising. That's let each business figure that out. Currently, a discount appliance store is selling 200 large screen TVs monthly. If the store invests X $1,000 in an advertising campaign, the ad company estimates that monthly sales will be given by n of x equals 3x to the third minus 0.25x to the fourth plus 200. Let me just, and now x is between 0 and 9. Why is x between 0 and 9? Why is that? Now, the reason we're restricting x between 0, well, obviously it has to be greater than 0 because we're talking about positive spending. They're not paying you to they're not paying you to run your advertisement. You're paying them. But as far as 9, the 9 is concerned, sometimes that could just be a restriction. It could be just they decided the budget is up to 9,000, or it could be something about the numbers or about the graphs or whatever. We'll see. We're actually going to see very quickly where this 9 comes from. So when when is the rate of change of sales increasing? When is it decreasing? What's the point of diminishing returns and the maximum rate of change of sales? I want to graph n and n prime on the same coordinate system. That would be nice. So, let's see. So n prime is 9x squared minus x to the third, which is x squared times 9 minus x. So right away we see where the 9 comes from, because when x is bigger than 9, then it's going to become negative. So the sales will actually decrease, which doesn't even make any sense. Why would more advertising decrease sales? Which just means that this model only works up to 9 months. To determine when n prime of x is increased, don't tell me that it gets to a point where people are sick of it. That's not. Anyway, to determine when n prime is increasing and decreasing, we find n double prime. That's a derivative, which is the derivative of n, and that comes out to be crunch, 18x minus 3x squared, which is 3x times 6 minus x. So now we want to analyze all the signs and everything. And here's what we get. Between 0 and 6, when x is near 6, then n double prime is positive, n single prime is positive, which means because n double prime is positive, n single prime is increasing, and because n prime is positive, then n of x is increasing, and because n double prime is positive, that's why we have concave up. So that's that. When x equals 6, then the second derivative is 0, the first derivative is still positive. That means we have a local max. And the inflection, well, why is it a local max? Because the function goes from increasing to decreasing. That you really see that from these things here, and that's an inflection point. When it goes from concave up to concave down, we see that here as well. And there we go. So if we look at table 2, we see that n prime is increasing on 0,6, decreasing on 6,9. The point of diminishing returns is x equals 6. Not that sales aren't increasing at x equals 6, but they increase slower once they hit x equals 6. And that's the point of diminishing returns. Now, what the business is going to decide to do, they're going to stop advertising. That's up to the business. And there could be other factors and so on and so forth. And the specific numbers may make a difference also, but I'm just saying that that's the point of diminishing returns, not no returns, but diminishing returns. So if the store spends $6,000, so if the store spends $6,000 on advertising monthly, sales are expected to be 524 TVs, and sales are expected to increase at a rate of 108 TVs per $1,000 spent on advertising. Money spent beyond 6,000 would increase sales, but at a lower rate. And here's the graph of n double prime. Here's the graph of n prime, and that is that's the beautiful. Oh, you know what? We never actually graphed the original function, which is this guy right here. Now I did put that in decimal. It's very hard to see because see it goes up. When x equals 9, it hits the top. Now, if I zoom in on this, you can't see the whole graph, but that's kind of what's going on. Okay, everybody. Well, that is the end of that's the end of this section. It's been loads of fun. I cannot tell you how much I've enjoyed this, and I will see you guys next time. Bye.